All right, welcome to the Explainer. Today, we're going to talk about a technology that could, literally, change how we power our world. We're talking everything from deep-sea sensors to rovers on the moon. And the whole idea sounds like something straight out of sci-fi, sending power through a beam of light. Just think about it for a second. What if you could trade your phone charger for a laser? No more messy cables, no more searching for an outlet. Just seamless power, delivered right to your device through the air or down a super thin fiber optic thread. Yeah, I know, it sounds pretty out there, but a huge new breakthrough has just brought this whole idea way, way closer to being real. So let's get into it. Okay, so first things first, how does this even work? Well, the tech is called power by light, and honestly, the name pretty much says it all. The basic idea is actually beautiful in its simplicity. You take electricity, right? Then you use a laser to turn that electricity into a really focused beam of light. You shoot that light down an optical fiber, and then on the other end, there's this special kind of solar cell. It's called a photonic power converter that catches the light and turns it right back into electricity. Simple as that. So yeah, you can really break the whole thing down into 3 super simple steps. Step 1, a laser makes the light. Step 2, an optical fiber, yep, the same kind you get your internet through, sends the light on its way. And finally, step 3, that photonic power converter, or PPC for short, turns the light back into juice. So you might be thinking, okay, cool, but why bother? We have copper wires. Well, here's the thing. Light has massive advantages. Optical fibers? They don't care about electromagnetic interference. They're also crazy lightweight. And here's the real kicker. They don't spark, ever. That makes them perfect for really sensitive places, like, say, inside a plane's fuel tank, or for super delicate medical gear. So if this is so great, why aren't we using it everywhere already? Good question. For decades, there's been one massive roadblock, and it all comes down to efficiency. Okay, so check this out, because this was the real head-scratcher. The absolute best kind of light for sending power down a fiber optic cable was, wouldn't you know it, the absolute worst kind for those special solar cells to turn back into electricity. It was this fundamental mismatch, like trying to catch tiny fish with a giant net. You just lose almost everything. And we're talking about a very specific range of infrared light here. This is the absolute sweet spot for fiber optics. It's this magic window where light can travel for miles and miles and barely lose any of its punch. It's the perfect messenger for carrying energy over long distances. So what did that mean in practice? It meant that no matter how much power you blasted down that fiber, you were guaranteed to lose more than half of it at the very last step. An efficiency rate below 50%, that just made the whole thing way too expensive and totally impractical for pretty much anything you'd want to use it for. It was a deal breaker. But then, a team from the University of Ottawa and Germany's Fraunhofer Institute decided, you know what? We can crack this. And they came at the problem with a totally new blueprint for how to build these things. So what was their secret weapon? Instead of just building stuff and hoping for the best, trial and error, they built this incredibly smart computer model, a predictive model. It let them design and tweak the perfect device inside a computer, getting every single layer just right before they even thought about actually building it for real. And what their model designed was something called a multi-junction photonic power converter. The best way to think about it is like stacking a bunch of different fishing nets. You've got one for big fish, one for medium fish, one for small fish. Each layer of this device is like a different net, perfectly tuned to catch a specific size of light energy. The end result? Almost no light gets wasted. It all gets caught and turned into power. So, armed with this perfect virtual blueprint, the team went and built the real thing. Their goal was simple but ambitious: smash that 50% barrier once and for all. And, well, the results were, frankly, staggering. They didn't just squeak past the old limit. No way. They completely shattered it. They set a brand new world record for efficiency in this exact, super important wavelength range. 53.6%. That's the magic number. For the very first time, a device, just running at normal room temperature, blew past that 50% wall. It converted more than half of the light shot at it directly into usable electricity. And you've got to understand, this isn't just a tiny little improvement. This is a massive leap. It completely rewrites the rules for this technology, making it not just possible, but practical and even economical. And if you're curious about the nitty-gritty, here are the specs. This is a real thing, a 4-junction cell made of some pretty complex stuff, indium gallium arsenide phosphide. But the key is, it's been tested, it's proven, and it delivers a really useful output of over 2 volts.
So, a world record is awesome for the scientists, but what does it mean for you and me, for the real world? Well, this is where things get really, really exciting.
All of a sudden, a whole bunch of applications that were just pipe dreams are now totally possible. We're talking about sensors on wind turbines that are completely lightning-proof, fuel gauges inside jet engines that can't possibly create a spark, sensors deep in the ocean that you never have to pull up to change the battery, and yeah, even a better way to power rovers on the moon and satellites orbiting Earth. And get this is just the beginning. The very same computer model that designed this record breaker, it predicts that with a few more tweaks, future designs could hit efficiencies as high as 67%. Think about that. That's converting nearly 2/3 of the light's energy straight into electricity. That's a game changer. So that's the real takeaway here. This isn't just about making an old piece of tech a little bit better. No, this opens up a whole new frontier. It leaves us with a huge, exciting question to think about. When we can send power safely and efficiently to literally any place a beam of light can reach, what are we going to build next?